Okay, ladies and gentlemen, 1.4, the method of elimination. So we're talking about linear systems, which is dealing with two linear equations at the same time, looking at them together, and we're trying to find where those lines intersect. That's called the point of intersection. If you're not dealing with lines, or for instance, the variables aren't x and y, then it might make more sense to think about the answer in terms of find the solution. Okay, you're finding the value of each variable that fits into both equations, that satisfies both equations. We've learned two ways to do it so far. We've said we can graph the lines and then just look and find the point of intersection. You don't need to write this down in the notes. This is just an intro. And we yesterday did the method of substitution. Substitution said if I have a couple of variables in equation 1 and I have the same two variables in equation 2, then I can actually just substitute y from equation 1, the value of x for y or y for x, it doesn't matter in this case because it's a simple equation here, and I can sub that into equation 2. And what will that do? Well, it'll make one of my letters disappear. I'll be left with one variable, one equation, which I can solve using simple algebra. Okay? Today, we're talking about the method of elimination. So we'll get into this, and the basic definition is just solving a linear system. Solving a linear system by adding or subtracting to eliminate. Solving a linear system by adding or subtracting to eliminate one of the variables. Why do I need three different methods? Well, the graphing method stinks. Okay? Unless you're on a computer, the graphing method is not super helpful because it only works really well on whole numbers. And it's kind of tedious. The method of substitution is really helpful if your equations are set up nice, like you have y or x isolated on a side already, or you can manipulate it to get an equivalent equation where that is true. Method of elimination, it doesn't matter how complicated the linear equation is, as long as you can line up your equations, it's pretty easy to work with. Okay? So we're going to go through a handful of examples. They start pretty simple and straightforward, and then they get a little more complicated. So we're going to learn little tricks along the way, building off of this first example 1, where we have the linear equations 3x plus y equals 19 and 4x minus y equals 2. Now, I've already lined them up on mine, and yours is lined up as well, but you're going to need to rewrite it where you have more space. So we're going to solve this system, which means what?
Find the x and y.
Find not the x and y intercepts, but the x and y coordinates of the point of intersection. So we're also, another way to say that is we're finding the x and y that will satisfy equation 1 and satisfy equation 2. Step 1 is the same as before. Label your equations. Now, in elimination, just like our definition said, we're going to add or subtract one equation from the other equation. So that's why we did 1.3 before doing lesson 1.2 and 1.4, because you need to know how to add and subtract equations, which was part of your investigation in that lesson. So I'm going to subtract or add one of these equations from the other, and the goal is to eliminate one of the variables. So we're just going to walk through this example. I'm going to draw a little equals line there. And I look at this and I notice that I have a positive y in the first equation and a negative y in the second equation. So if I add those up, they'll cancel out. I'll have 1y minus 1y, which is 0 y's, which will eliminate the y's. Okay? Now you know that if I add and subtract an equation, I'm going to get a third equation. And what's going to be true about that third equation?
It has the linear system.
It has the same solutions. Okay? So I'm going to create a third equation. It's going to have the same solution as the original system, but it's only going to have one variable. Well, that's helpful because I can solve one equation, one variable. So let's see what happens when I add these up. Okay? So equation 3 here is going to be 1 plus 2. Now, this is a first example. It's pretty easy, but you can see that my x's are lined up, my y's are lined up, and my constants are lined up. Turns out it doesn't matter which order they're all in. Okay? We'll get different equations where they're in different orders, or maybe they're all on one side and there's a 0 on the other side. Doesn't matter as long as these things are lined up. So I line up my x's. I have 3x plus 4x. How many x's? 7 x's. 1 y, take away 1 y. No y's. I'm going to just leave that out. 19 plus 2. Huh. What's x? 3. Okay. Now, because of what we learned the other day, that I've created another equivalent system, that the solution for any system involving equation 3 is the same as the solution for 1 and 2, I know that the solution for x, part of the solution, because I need an x and a y, but I know that the x from these equations are going to be 3. Okay? What's the next step?
Plug it into one equation.
Plug it into either equation 1 or equation 2. I'm going to backtrack and just give you a little bit of note here. I'm going to add equation 1 and 2. I did that because I noticed I had an opposite sign in front of my 1y. Now I'm going to sub x equals 3 into equation 1. Doesn't matter which one I use. 1, I'll just put a note for you, or 2, so that you don't forget. You could do it in either one. I'm going to take equation 1 because it's the top one, and I've got 3x, but now I know x is going to be 3 at the point of intersection, plus y. I don't know what y is yet, but now I have a situation where y is the only missing value, and if I only have one missing value, I can solve it. 3 times 3 is 9. Subtract 9 from both sides. Y equals 10. Okay? So I'm assuming that the solution is x equals 3, y equals 10. If I want to write that as coordinates, I can. It's 310. Therefore, 310 is the POI, point of intersection. And the last thing it asks us to do is check. Okay, so to check this, I'm using right side, left side. So I've got left side in equation 1 is 3x plus y. Right side is 19. Replace my x and y with 3 and 10. Work that out. 9 plus 10 equals 19 equals right side. I'm going pretty quick here, but that's okay. I'm going to do the same thing in the second equation. Left side is 4x minus y. Right side is 2. Sub in my solution. Okay. 4 times 3 is 12, minus 10 is 2. Equals right side. So it checks out, means I did it correctly. Quick review on the basic strategy. 2 equations. I want to eliminate one of the variables by adding or subtracting one equation from the other. Okay. So I added them because I noticed I had opposite signs in front of y. Another key that we're going to realize too, the value in front of the y needs to be the same. In both cases, I have 1y and 1y. Because it's positive and a negative, I added. That eliminated the y's, left me a really easy 7x equals 21 to get my first variable. And then I'm following the same steps as I did yesterday. Sub that back into one of the originals and to find the second one. Okay? Example 2, it's going to be the exact same strategy, but we're going to add one step on the difficulty level. So we've got 10x plus 4y equals -1. And then we have 8x minus 2y equals 7. Step 1, label. 1, 2. All right, I know I want to add or subtract one equation from the other in order to eliminate a variable, but I'm looking at these, and if I add them, don't write this yet, if I add them, I'm going to end up with 18 x's, and I'm going to end up with 2 y's. That's not going to eliminate anything. If I subtract them, I'm going to end up with 2 x's and 6 y's. Well, that didn't eliminate anything either.
But if we multiply them,
I can take one of my equations, right, and I can create an equivalent equation that then I can work with, okay? So I'm going to go ahead and say, because my numbers are bigger in equation 1, like I have 10x and 4y, do you see a way I can get the same number in front of the x's or in front of the y's? Yeah, I'm going to take equation 2 and I'm going to multiply it by 2, okay? So in order to do that, I'm going to take equation 2, and I'm going to say what I'm doing. I'm going to go 2 times equation 2. So now in my work, I can clearly see what I did, and I can trace down the result. Now, how do I multiply an equation by a constant?
you just increase everything.
I have to multiply every term by the same constant. So if I'm multiplying by 2 in equation 2, I need to do it to every term. So I'm going to end up with 16x's minus 4y's, and that's going to equal 14. Same thing to both sides. Make sense? So I actually haven't changed the linear relationship in equation 2. X and y still relate to each other in the exact same way. Okay? There's still going to be this, if I graphed this equation 2 and this equation 2, they'd be the same line right on top of each other in Desmos. Okay? I've created an equivalent equation, helpful tool. Now I can take equation 1 back down here. Equation 1 is 10x plus 4y equals -1. Some of your brains just got incredibly frustrated because I now have equation 2 on top of equation 1, and you're thinking, oh, why'd you do that? Can't do that. Sure you can. You can do whatever you want, as long as you play within the rules. So now that I have the same numeric coefficient in front of y, I notice that the signs are opposite. That's going to tell me whether I'm going to add or subtract. What am I going to do in order to eliminate one of the variables? I'm going to add them. Okay? When I add a negative and a positive that are opposites, I get 0. Okay? If you subtract opposites, you will not get 0. So this is an adding situation. And I see already my x's and my y's and my constants are nicely lined up. So I'm going to go add my x's. That gives me 26 x's. -4y plus 4y, that cancels out. And then I have 14 plus -1. 13. Okay, it's just 14 minus 1. All right, they've given us some nice numbers here. I'm just going to identify one grave danger that lots of you are going to do this. You're going to say, oh, that's easy. X equals 2. Is that true? Sure isn't. Okay, 26 divided by 13 is 2, but that's not what you have. You have divide both sides by 26. You have x equals 13 over 26, which reduces to 1/2. Okay? Step 1, done. Now what do? Same as before, we pick one of our equations. By the way, yesterday you manipulated an equation, and then that equation was actually easier to use because it isolated a variable. Today, would you rather use this equation 2 or this equation 2?
The first one.
You'd rather use the original because it's smaller numbers. Okay, so let's do that. Let's sub it into, we can do that. Let's sub it into equation 2. So I know x is 1/2, so I'm going to have 8 times 1/2 minus 2 times y equals 7. Notice the only thing I did was sub in x for x. Okay, the rest of it is just a copying game. Step by step, play within the rules. Don't let your brain go off the rails and do something crazy. Only do what you're allowed to do in math. There are rules. Once you learn to play within them, you can do a lot of wonderful things. Okay, so let's simplify this. I've got half of 8, 4. I've got negative 2y equals 7. What should I do now?
Minus 4 from each side.
Subtract 4 from both sides. That's going to leave me with negative 2y equals 3. Now what?
Divide both by negative 2.
Divide both sides by negative 2. Do you need your calculator for that?
No.
No, you don't, because you're not going for decimals. Okay, you're going for fractions. It's really easy. What's 3 divided by 2? Well, 3 divided by 2. Done.
Oh, yeah.
Okay? Make sure you keep that negative sign. You're dividing by a negative. So on the left, the negatives are going to cancel out, leaving you with positive y. But on the right, 3 divided by negative 2 is going to give you a negative solution. There's your 2 solutions. All right, and I'm not going to show you how to check on this one, but you could go ahead and go left side, right side for equation 1 and left side, right side for equation 2. And then you would get the solution to the linear system is x equals half and y equals negative 3 halves. That is the solution. You need both of those in order to have a full, complete solution, okay? It's not like this is one solution and this is another solution. No. Together, they form the solution. Okay? So if you were to graph this line, and this line, and this line, they would all go through the point 1/2, negative 3 halves. Okay?
Smart.
Okay. Example 3. Example 3, again, it's the same thing. It tells us to find the point of intersection using elimination. The linear system involves the line 4x plus 3y equals 13, and the linear equation 5x minus 4y equals negative 7. All right. We got equation 1 and equation 2. What would you like to do? Do I have any coefficients that are the same? Do I have the same number of x's in both equations?
No.
No. Do I have the same number of y's in both equations? No. So I need to change at least one of the equations. Can I change one of the equations and create an equivalent equation in such a way that I will have the same coefficient?
No.
If I just change one of them? Can I multiply 3 by anything in order to get 4? Nope. Can I multiply 4 by anything in order to get 5? Nope. So I need to change both equations. Okay? So now I need to make a decision. I'm going to either eliminate the x's by making these the same value, or I'm going to eliminate the y's by making these the same value. Which would you like to do?
Well, the wise.
Why?
That was funny.
Okay. One of them is negative, which means I'll be able to add the equations. By the way, if I'm going to do, maybe I should show you one where they're positive. So I'm going to actually do the x's. In this case, I would do the y's because they're smaller numbers. Because to get the y's equal, I need to multiply equation 1 by 4 and equation 2 by 3. Okay, which gives me 12y and negative 12y. But I'm actually going to do the x's. The lowest common multiple between 4 and 5 is 20. So I need to multiply equation 1 by 5. And I need to multiply equation 2 by 4. So you're talking about lowest common multiples. Again, I would choose to do the y's typically because they're smaller numbers. Smaller multipliers is going to give smaller numbers across the whole problem. But because I want to show you one where there's subtraction involved, I'm going to do the x's. Okay, so I need to multiply everything in equation 1 by 5. 5 times 4 is?
20.
It's going to give me 20 x's. How many y's? 15 y's. And the constant at the end? 65. If you need a calculator for that, that's fine. Use your calculator. Don't make silly mistakes. Okay. Equation 2. 5 times 4 is?
20.
That was the goal. How many y's do I have?
60.
Negative 16, and that's going to be really helpful. Look what's going to happen here. I'm going to be left with positive 1y. That's nice. Oh no, I'm not. Never mind. Scratch that. Reverse it. And the last one, negative 7 times 4?
Negative 28.
Negative 28. Okay. So it looks a bit ugly. They're bigger numbers. But I'm just going to use the exact same strategy, okay? But this time, I have positive 20 and positive 20. So I'm going to need to subtract. Okay? Be careful. You may use your calculator. Carrying on, now I'm going to subtract equation 2 from equation 1. So I've got 20 x's, and I'm going to take away 20 x's. 0 x's. Then I have 15 y's. Careful. I'm going to take away negative 16 y's. What happens when I take away a negative? It's a positive. Okay? Negative, negative, that's a positive. So I actually have 15 plus 16, which is 31 y's. In the same situation here, I got 65 minus negative 28. That's 65 plus 28, which is 93. Okay, you can use your calculator for stuff like that. Just make sure you're using the signs. Typically, if I'm using my calculator for something like that, I would just do the numbers. I would just do 65 plus 28, or no, I wouldn't. You'd have to think about this, that negative negative is a positive, 65 plus 28. And y equals?
3.
All right, there's one of your solutions. Now what do I do? Sub it back into equation 1 or equation 2. I'm going to use equation 1. I get 4x plus 3 times y, which is now 3, equals 13. And I can work that out. 4x plus 9 equals 13. Subtract 9 from both sides. Divide both sides by 4. X equals 1. And again, you could go and check that in both equations, left side, right side, or you can just try to do it mentally. So if I stick a 1 in here, I get 4 plus 9. 4 plus 9 is 13. So that one checks out. If I stick a 1 in here, I get 5. If I stick a 3 in here, I get negative 12. So I got 5 minus 12, negative 7. Yeah, that one checks out. That confirms that this is a solution to the problem. If I had to give the point of intersection, which I actually do have to do, I would have to write one more statement. Therefore, 1, 3 is the point of intersection. So again, this time I needed to create an equivalent equation for equation 1. I needed to create an equivalent equation for equation 2. Because 1 is equivalent to 1 and 2 is equivalent to 2, I haven't changed the solution. The system still has the same solution. But now I have a matching coefficient, so I can eliminate my variable x, solve for y, come back to one of the equations that has x in it still, solve for x, double check my answer, write what the problem actually asks me to write, which is a point of intersection, and bada bing, bada boom, done. So in example 4, we're given a word problem, and we're going to have to, just like every other word problem that we do, we're going to have to introduce variables, and we're going to have to set up our own equations. Okay, you are going to need to know how to do that by the time we have a test here in this course. So let's, if you're there, please read it, and you might want to underline some key information. We have a small store that sells CDs and DVDs. Do you guys even know what those are anymore? All right, all right. The CDs, so this is one store, okay? I'm just going to jot down my important information. I've got CDs sell for $9 each. DVDs sell for $11 each. Cody is working part-time. Cody sells $204 worth of CDs and DVDs during his shift. He also knows that 20 items were sold. And he needs to tell the store owner how many of each type were sold, but he can't remember. He doesn't know how many of each type. He just knows, okay, I sold 20 things and I made this much money. Okay? But guess what? How many variables are there in this situation? CDs, DVDs. 2 variables. How many equations are there? He knows how much money he made. There's an equation. And he knows how many items he sold. There's another equation. So we have 2 variables, 2 equations. So let's set this up. Step 1. Let statements. Introduce your variables. Let statements. Okay, you do need to know how to do this. Well, our variables are CDs and DVDs. So let's let C represent, and I have to be specific here. I want it to represent the number of CDs sold. That's key. All right? Which means D is going to represent the number of DVDs sold. Have you ever seen this before? This just means same as above. Okay? I'm just taking those words down. CDs, DVDs, the sentence is the same, but I have C for CDs and D for DVDs. Good. What's my next step? Set up 2 equations. Now there's one really easy equation and there's one slightly more difficult equation. Go ahead and read those sentences again and see if you can give me one of the equations. Good, so our first one comes from the number of items sold. He sold 20 altogether. So we know that C plus D equals 20. The number of CDs sold, right, plus the number of DVDs sold will be 20 items total. Now the second equation is a little bit more challenging, and it relates to the amount of money that he earned, or the profit that he sold there, the revenue. It's going to add up to $204. But how do we get there? I can't do C plus D again. I'm talking about dollars. You want to give it a shot?
9C plus 11.
Yeah, I know every CD he makes, every CD he sells, going to make $9. So that's what this says. 9 times C. The number of CDs, $9 each. There you go. Number of DVDs, $11 each. There you go. Okay? So when you're doing these word problems, this is an easier one. You're going to get harder ones in your practice problems. You're going to have to take out the variables and look at the sentences. What do I actually have here? And the money ones are always going to be the number added up and then the values added up. DVDs are $11 each. CDs are $9 each. All right, here we go. Now when you're doing a test, you'll probably get to choose. Do I want to do substitution, what you learned yesterday, or do I want to do elimination? In this case, I'd probably lean toward substitution because I already have a C and a D by themselves. I just subtract D from each side and then I'd be able to substitute. But we're going to do what this lesson asks us to do. We're going to use elimination. What do you notice? Can I eliminate right off the bat? I cannot. What do I need to do?
Multiply together.
I'm going to multiply equation 1 by
9.
so that
The C's are gone.
I can eliminate my C's. Make sure I multiply all of equation 1 by 9. Okay? I switched colors. That's kind of a little bit confusing. I probably shouldn't have done that. But now I'm in a situation where basically I'm just ignoring this thing. Okay? I have my 2 equations. They're lined up, equation 1 and equation 2. Make sure you don't actually accidentally have equation 1 and equation 1 or equation 2 and equation 2. That won't work. Okay? But now I do have a situation where I have the same coefficient in front of the C term. So what am I going to do? I'm going to subtract. Because 9 take away 9 is 0. 11D take away 9 of those D's. 2 D's remaining. 204 take away 180. How many DVDs did I sell? Okay. Next step, sub it back into one of my equations. I'm going to choose equation 1 because that's real easy. And I might not even show it in my work. I might just say, Mr. V, this is so easy, I don't even have to show it. How many CDs did this guy sell? Sorry, did somebody say 8? Okay, because it's a word problem, I need to respond in words. Cody sold 8 CDs and 12 DVDs during his shift. Okay, there's a last little note that is on the bottom of your notebook that I would like to take care of right now, and it is, how do two lines interact with each other? What are the possible solutions for a linear system? Okay, so I'm going to draw that chart out quickly, and we'll talk through it. We've got types of lines, types. We've got a diagram. We've got an inference we can make about their slopes. We've got something we can say about the y-intercepts of the two lines and the number of solutions. Okay, you know this a little bit already because you ran into this problem yesterday, but the words that are given already, we'll just look at that top row. If there is one solution, okay, what does that mean? By the way, let me just give you your 3 options. Your 3 choices are intersecting, parallel, or coincident. If there is one solution, which one of these pictures has one solution? Okay, the intersecting one. So go ahead and just draw any 2 lines that intersect. They don't have to intersect at a right angle. Those 2 lines, that linear system, has one solution. Those 2 lines will never, ever, ever, across the entire universe, meet each other again. They said hello, then they said see you later. Okay? One solution. What is true about those slopes? Are they the same or different? Different. Do they have to be different, or could they be the same? They have to be different. Okay? They will always be different. If you need help with that, you can write always different. What about their y-intercept? Could it be different?
It could be the same.
Could be different and could be the same. What would it mean if it was the same?
It would be
Cross.
The
parallel.
y-intercept would be the
Yeah, it means that point of intersection would be the y-intercept as well. It means the x value will be 0 for your point of intersection. Okay? So y-intercept, either or, could be same or different. What's the word for that? Intersecting. Okay, those lines are intersecting. In the next row, you're told that the linear system has 2 linear equations in which the slope is equal. You need this word too for the next row, coincident. So yeah, it's going to be parallel.
or it's gonna be the same one.
Yeah, but it can't be because that's what our next row is going to take care of, coincident. So here, you're right, we're going to have parallel lines. Parallel lines have equal slope, okay? Parallel and distinct. That means not the same line. So parallel and distinct, that is what separates it from being coincident. Because if I'm working with parallel lines that are not distinct, that means they're actually coincident. Okay, we're not necessarily always going to say parallel and distinct. We're just going to use the word parallel. Diagram for parallel, doesn't matter what your first line looks like as long as your second line is beside it and looks the same. Okay, going the same direction, equal slope, same direction. What can you tell me about the y-intercepts of these lines?
They're never the same.
Never the same. Cannot be the same. What would happen if they were the same?
They'd be on top of
It'd
each
be
other.
coincident.
They'd be coincident. Okay? So different. How many solutions?
1,
0.
Do they ever have a point of intersection?
0.
Impossible. Across the whole universe, they will never touch each other. They won't even get closer to each other. Ever. Okay? Okay, last one. Coincident. You already kind of know what that means, so what could you draw? Just one line. If you want to use two colors, you could kind of do it like a dotted line right on top to show that you do actually have two lines here. Okay? What can you say about the slope?
Equal.
Equal. Has to be.
Yes.
Y-intercept?
The same.
Has to be.
Yes.
Solutions?
1.
Eh.
Actually.
Infinite.
Infinite.
Okay, that's where you get into this situation. 0x equals 0. That's always true for any value of x, no matter how far you go this way or how far you go that way along your y-axis. Everything is a solution. They're on top of each other the whole time. Infinite number of solutions. If you don't know what that sign means. Okay, so 3 options for the solution to a linear system. It either has 1 solution, 0 solutions, or an infinite number of solutions. If it has an infinite number of solutions, it's the same line. You should have figured it out before doing all the math work. If it's parallel, it will have 0 solutions. Another thing you can probably see most of the time before you try to solve it. And then if it's intersecting, you'll be able to solve it 1 solution. If you solve it and there's 1 solution, they intersect. Okay? Your practice problems. You can find your practice problems on page 30. You are responsible for 1 through 3, 5, 7, 8.